As she said, my name is Mark Seiss. I'm a data scientist with Dun and Bradstreet. By education, I am a statistician. Most of my work at Dun and Bradstreet has to do with working in client-facing capacity, working with our clients to first define their problems, but also show them how they can use data and analytics to solve their business needs. When I joined Dun and Bradstreet 5 years ago, most of the models we built were standard scorecard / logistic regression models. But most recently, Dun & Bradstreet started investing in talent and infrastructure to start implementing ML models. So as a client-facing person that works at Dun & Bradstreet, our clients ask very standard questions or very intuitive questions about machine learning models. How many records do you need to build a model? Well, more. Okay, what's that mean? So I actually thought those questions as well. So I'd ask somebody in our group, well, how many do you say when somebody asks you that? I don't know, 100,000. Doesn't really seem very satisfying to me, so I started doing research into what are answer those questions where we can very intelligently answer those questions. So that's what this research is about, so just go into it and give you guys a description. So the agenda is we just give an introduction. Again, I just gave you a pretty big high-level summary, a little bit more information on what the motivation for this research was, what questions we explored. So one of them is how many records do you need to build a good ML model? But there are 3 other questions as well in that research. Data, what do we use data? So what data do we use? So at Dun & Bradstreet, we have a lot of data available to us in terms of business data. We have our clients' data as well. So just giving you guys a description of what that data is and what kind of data we did for these experiments. Analysis experiments is just going through 4 different questions I asked in the experiments we did, and what kind of conclusions did we come up with based on that research. And then summary recommendations. These are the recommendations I'm going to give to my colleagues. It's not by far not done yet, so this is the first iteration of this research. The findings in some cases aren't concrete, but as we again do more experiments, more findings that support the conclusions we make, they become harder and more sticky in terms of recommendations. I also want to give thanks to Venkata Viparthi. So I'm not the only one who's doing this research. My colleagues at Dun & Bradstreet, but in particular Venkata Viparthi, gave me a lot of help and a lot of contributions to this research. So I just want to give him a call out about this. So what's the motivation? For traditional models, we have kind of a rubric about what steps we should follow to build say, a logistic regression model. You go through usual steps, say segmentation analysis, univariate analysis, variable selection, explore interactions, you do a model validation, then you finalize the model. These are stuff that people at analysts at Dun & Bradstreet all follow. They have their own little flavors to each step, or they might introduce some other things, but everybody basically follows these 6 steps. For machine learning, some of these steps don't really make sense, do they? So segmentation analysis, does that make sense? That's actually one of the questions we're going to ask as part of this research. Does segmentation analysis make sense when you're building ML models? In traditional models, it does, maybe not for ML models. So I just want to come up with some kind of similar rubric for our analysts at Dun & Bradstreet that we all should follow, and guidance on those questions I referred to earlier that our clients are asking. The guidance that we get for ML models, like I said before, it's mostly just anecdotal evidence. Well, this guy said this, or in general, I follow this rule. But what exactly is the rule for it, or what exactly recommendations should you have? There's not a lot of literature out there, so I went around looking for literature on these kind of recommendations. Didn't really find a lot, so that's why it brought me onto this research. And again, how to answer queries. So what are the actual questions we explored in this research? These are 4 of them. We explored other questions as well, but these are the basic 4 I'm going to present today. How many records do you need for ML models to outperform traditional models? Usually we say more. What exactly is that number? And what do we say to clients when they ask? Should the pool of predictor variables be filtered prior to inputting ML models? General guidance is you just throw everything in. Let the models pick out which is important, what contributes to the model, but it's actually the best way. Should you be filtering it? Because when you do traditional models, you filter the variables, you get it down to a reasonable set, then you build a model, say, with a stepwise regression model. But is that the same thing with ML models? Does segmentation improve the performance of models? General guidance is that say your random forest or your GBM model will decide which splits are the most important. You don't have to do segmentation because it's a tree-based model. But is segmentation important in terms of ML models? Because you do have to do it when you do traditional models. And the last question is mostly about how does the univariate performance of univariate performance distribution affect the lift of the models. Most of that has to come with, so every time we build a model at Dun and Bradstreet right now, we're building ML models on the side of it, just to compare the performance of that traditional model to an ML model. In some cases, the ML model doesn't really do much better, and we want to know why, because obviously ML models generally do better. The complex interactions, the complex relationships you can capture with them generally provide you lift, but in a lot of cases we didn't see much lift. We were wondering why. One of the hypotheses I had while this was you have some variables that are much more predictive than others. It might not give you as much lift as you think. So there's a slide about that as well. What data we use? Just a quick summary about what data we use for this analysis. Alternative lenders data, so we do research with respect to how we can give guidance to alternative lenders or lenders that provide financing to businesses that otherwise can't get loans. Usually these decisions are quick. Usually they turn around these decisions in 24 hours to 48 hours, and it's whether a company is going to be delinquent in their loan payments or not. Our financial stress score at Dun & Bradstreet is one of our core capabilities or core offerings to our clients. And it measures the likelihood that a business is going to go out of business or bankrupt in the next 12 months. We have these in 20 of our markets, especially, particularly the US market. But one of the key things about this data set is that it's split in two segments, small companies and large companies, and that will come in when we talk about segmentation analysis. The last two are projects I actually particularly work on. Canadian export propensity score. We want to be able to provide our Canadian customers or Canadian government with insights into what companies are exporting, which ones aren't exporting. It helps with planning. It helps with economic development where they can target businesses that are about to export or export and encourage them to export if they're about to. And SBA, so the Small Business Administration in the United States, we have a large engagement with them where we help them with their analytics. One of our core offerings for them is called a lender purchase rating. What the SBA does is they encourage banks to provide loans to businesses, in which case they guarantee the loan if it were to go bad, which is called a purchase. So if SBA purchases it, it's obviously a bad situation for SBA. In 2008, they had a large amount of purchases right through 2008 to 2010. So they want to be able to monitor risk in their portfolio and they want to monitor purchases in their portfolio. So these are 4 data sets. These are just the real world data that we're testing these hypotheses on. Just give you a summary overview of those. So what's the first hypothesis? So how many records do we need? This is really the basic question I get from customers when we're talking about ML models. Well, I need more data. Well, how much is that? The way I approach this is looking at the FSS small business data set. There's about 1.1 million records in it. It's got about 4% bad rate. And I've randomly sampled from that. And we randomly sample 1,000 records, 10,000 records, 50,000 records, 100,000 records, 500,000 records, and 1 million records. Build an ML model, built a GBM model, build a random forest model, build a scorecard model, and compare the performance of each of the models on those amount of records. And what we get is the performance here. So what we find is that the scorecard model performs better than both the XGBoost and the random forest model for small amounts of records. So for 5 and 10,000 sample records, scorecard traditional model does better. Once we get to 50,000 records, the XGBoost does better. Random forest a little bit better than scorecard method. But the most interesting thing I thought from this was, first is about 50,000 records is when you find the ML models do better. But when you get more records towards the end there, when you get 500,000 records, 1 million records, performance of scorecard models actually do worse. You see a very large decline. And a lot of that I think has to do with you start getting your p-values start becoming significant because you have just so much data. You start incorporating signals into the model that you otherwise shouldn't be. So that was actually one of the interesting things. And it kind of follows from, actually my manager did this kind of research for his dissertation, and it kind of jives with what he found as well. So it seems like about 50,000 records, but is that actually the question should we be asking? How many records are there that we need to build an ML model? Or is the question, how many bad records do we need? Is it the number of records, or is it the number of bad records, or the minority class in your dichotomous response variable? It turns out it's the number of bad records is actually the more important number you should be quoting. Because when you look at the graph, so what I did was I randomly sampled, not just randomly sampled from the full data set, but randomly sampled good records and bad records, and created data sets with different bad rates in them. So I did a 1% bad rate, a 10% bad rate, and a 25% bad rate, sampling, say, 1,000 records, 10,000 records, 100,000 records, and compared the performance of the models. When you look at the total number of records, you see for the XGBoost on the left, you see that as the more records you get, the better it performs, but there's a distinct difference in the performance based on the bad rate. So you can have a 10,000 records, and you have 25% bad rate, it does much better than 10% bad rate, does better than a 1% bad rate records. So you see performance isn't exactly really that tied to the number of records, whereas if you look at the graphs to the right for the XGBoost and random forest, you see a very tight curve, where the number of bad records is the performance is very correlated to the number of bad records, where bad rate doesn't really matter, whereas the number of bad records does matter. So that's what we're really finding on this one, is that the number of bad records is actually what you should be quoting for your clients. And what's that number? What's that number of bad records? Right, so we look at the number of bad records, we compare the XGBoost, the scorecard, and the random forest, and that number is about 1,000. So ML models start outperforming the scorecard models at about 1,000 bad records. Regardless of how many total records you have, number of good records, about 1,000 bad records, you start to do better. And we saw that XGBoost actually does outperform the random forest in general in this simulation. When I showed this to my colleagues, the one thing they were looking at was this curve, what's going on here. So this is the scorecard model. And what this is showing is that the more records you have isn't exactly better for when you build a scorecard model. So I highlight 2 points where you have 10,000 bads in both cases. But in one case, you have 100,000 total sample. The other case, you have 1 million total sample. And generally beforehand, yeah, 5 minutes? Okay. And generally beforehand, I thought, hey, you need more records to build a better model. That's not always the case. If you have more records in this case, the model does worse. So that's the guidance we give our clients based on this research, is you need 1,000 bads, and more records isn't always better in terms of scorecard models. The hypothesis, too, is should we filter predictor variables before we input them? And what we did is we leveraged the alternative lenders data, which had about 1,000 different variables in it. So from all the data sources, the variables weren't pre-filtered. So we had 1,000 variables to assess. And we applied 3 different filtering methodologies. First, we took all 1,000 variables, just put it into a random forest, put it into XGBoost, and tested performance. We did a univariate performance metric, so we used the Gini coefficient univariately, calculated it, rank ordered the variables, and took the, say, top 150 or so. We did an initial ML model run, used the variable importance, selected the top 150, and we did traditional filtering, which is the univariate performance metric, plus missing rates, plus variable clustering. And again, took the top 50 variables from that. What we found is that filtering of some sort does better. So this isn't the most solid conclusion we have yet. So this is something we're going to reevaluate as we go. Apply this to more cases or more data sets. But in terms of XGBoost, the univariate performance metrics with top 150 did better. For random forest, the traditional filtering with the variable clustering and the missing rate and the univariate performance metrics did better. But this is probably the least solid of the ones I'm presenting here, and this needs more attention to get a more solid recommendation. Hypothesis 3 is, does model segmentation apply? So for traditional models, that's one of the first things you look at. For ML models, that makes sense. Recommendation from previous user is, no, you don't need to do it, because random forest or XGBoost model will pick that segmentation from the model if it's significant. What we found is that's actually not the case. So for the FSS data sets, we have the small and large segments. We built models in each of those separately. Then we built one combined model on the combined data set and compared performance. For XGBoost, the segmented model does better, where you get 78 Gini for the segmented model versus 77% Gini for the single model. And for the random forest, we see an even bigger lift. So 75% performance for the segmented model versus single model. So segmentation in this case does show improved performance. And the last hypothesis is, why is my ML model doing better? Like I said earlier, every time we build a traditional model, we build an ML model right next to it. Some cases it doesn't make sense to do an ML model because the interpretability just isn't there yet for our customers. But we built an ML model just to do for research purposes. So what we did for 3 different cases for the alternative lenders, the Canadian Export Propensity Score, and the SBA LPR model, we built ML models, compared them to the performance of the scorecard model, and measured performance. What we call is a relative lift, so what's the difference between them relative to the scorecard performance. And we wanted to see what scenarios does the ML model do a lot better than the scorecard model. What we find is in cases where the data set has one variable that performs much better univariately than the other variables, the ML lift isn't as important, or the ML lift isn't as big. Whereas if you have a more even distribution, say the first one where you see the alternative lenders, you don't see one or two variables that are much more predictive than the other variables. You see a lot less lift. You see more lift in those cases. And that kind of jives with what I heard from the Wells Fargo presentation earlier today, where they said if you have one variable that is nonlinear, those interactions don't really make too much of a difference. You can build a good model with just a linear relationship. That kind of jives with that. Again, you can see this is not the most rock solid thing, because you can see as the performance increases, you see less lift. But we need more study of this. But the first impressions are showing that if you have this kind of distribution, or a distribution where one variable shows more predictive than the others, you're not going to see a lot of lift in your ML models. And that gets to our recommendations. So summary recommendations are, again, we're trying to do more research to get this more solid, but you need about 1,000 BADs to build a good ML model that will outperform your scorecard model. Variables should be filtered. We're not quite sure which way you should be doing it, but they should be filtered in some way before you input them in an ML model. Segmentation does provide lift, so you should approach it the way you would with traditional models. And models showed less lift when there's one variable that is much more predictive, one or two variables that is much more predictive than just the rest of the variables in inputting your model. So that's my presentation. Thank you guys for showing up, listening to me. We have time for questions, or no? I went too long.
Yeah.
Okay, so if you want to ask me questions, I'll be around. So.
Thank you, Mark, for sharing the use case. Thank you so much.